Hi everyone, in this exercise, we're given three binary relations on the set of real numbers, and we're asked to determine if each of them satisfies the reflexivity, the symmetry, as well as the transitivity. So let us look at the first one, where a real number x is related to a real number y if and only if the product of x and y is positive. Now, for reflexivity, let us take 0, which is clearly a real number, yet 0 multiplying 0 is equal to 0 itself, which is not positive. So 0 is not related to 0, and we conclude that this relation is not reflexive. Next, for symmetry, assume that we are given two arbitrary real numbers, x and y, where x is related to y. By definition, this means that x multiplying y is positive. From there, we conclude that y multiplying x is also positive. After all, the multiplication of real numbers is commutative. Thus, y is related to x, and this relation is indeed symmetric. Finally, for the transitivity, given arbitrary real numbers x, y, z, where x is related to y and y is related to z. According to the definition, this means that xy is positive and yz is also positive. In particular, this implies that y is not equal to 0. From there, let us multiply these two positive numbers, which results in another positive real number, that is xy squared z. Now recall that y is non-zero, nor is y squared. Hence, dividing y squared on both hand sides, we see that xz is also positive, which implies that x is related to z, and this justifies the transitivity. We conclude that this relation is symmetric, transitive, but not reflexive. Next, let us look at our second binary relation, where a real number x is related to a real number y if and only if the product xy is non-negative. For reflexivity, given any real number x, we know that x multiplying itself is equal to x squared, which is always non-negative. In other words, x is always related to x itself. This justifies the reflexivity. Next, for the symmetry, assume that we're given two arbitrary real numbers x and y, where x is related to y. Again, by definition, this means that xy is non-negative. And by applying the commutativity of multiplication for yet another time, we see this means yx is also non-negative. Hence, y is also related to x, and this justifies the symmetry. However, for the transitivity, let us take x to be 1, y to be 0, and z to be -1. Direct computation shows that 1 multiplying 0 is equal to 0, thus x is related to y. Similarly, 0 multiplying -1 is equal to 0, thus y is related to z. However, 1 multiplying -1 is equal to -1, which is a negative number, and this shows that x is not related to z. As a consequence, the transitivity fails here. We conclude that this relation, although being reflexive and symmetric, is unfortunately not transitive. Finally, let us consider the last binary relation, where a real number x is related to a real number y if and only if either y itself vanishes, or the ratio of x over y is at least 1. Now, for reflexivity, let us take an arbitrary real number x, and we know there are two possibilities. Either x is equal to 0, in which case the first part of this disjunction holds, or x is non-zero. But if x is non-zero, we see that x over x is always equal to 1. Hence, the second part of the disjunction holds. Summarizing these two parts together, we conclude that x is always related to x itself. In other words, this relation is indeed reflexive. Next, for symmetry, we can take x to be 2 and y to be 1. With such choices, we see that x over y is equal to 2, which is clearly greater than or equal to 1. Thus, x is related to y. On the other hand, notice that y over x is equal to 1/2, which is strictly less than 1. Moreover, x is not 0 neither. Hence, we conclude that y is not related to x, and this binary relation is not symmetric. Last but not least, let us check the transitivity. To this end, assume that we are given arbitrary real numbers x, y, and z, where x is related to y and y is related to z. Let us focus on the value of z, and we see there are two cases. Either z itself is equal to 0, but if z is equal to 0, then x is already related to z by our definition. In the second case, z is not equal to 0. Thus, for y to be related to z, the only possibility is y over z should be at least 1, which in turn implies that y is not equal to 0 neither. But now that y is not equal to 0, for x to be related to y, the only possibility is that x over y is also at least 1. Multiplying these two inequalities together, where y cancels with each other, and we're left with x over z is greater than or equal to 1, which again indicates that x is related to z. Thus, in both cases, we have verified that x is related to z, and this justifies the transitivity. As a consequence, this binary relation is reflexive, transitive, but it is not symmetric. As a final remark, recall that an equivalence relation is a binary relation that is reflexive, symmetric, and transitive at the same time. Thus, none of the aforementioned binary relations is an equivalence relation.